Let's wait for 1 2 more minutes and then we can start. Okay, I guess we can start now. So good evening all. Welcome to the week 11 of our problem solving discussion session for the NPTEL course NOC 22C68 ground improvement. Like currently the course is being tutored by Professor Dilip Kumar Bedia, who is head and professor in Department of Civil Engineering, IIT Kharagpur. Myself, Rituraj Singh Sujat, I am Prime Minister's Research Fellow in Department of Earthquake Engineering from IIT Roorkee. So those who are seeing these videos for the first time, let me tell you, this 1 hour session is basically dealing with the interactive session with the learners. We'll be having the discussion of the important concept which you have covered in the last week of NPTEL sessions. We will also be having some sample questions which will help you in dealing with your assignment related questions. Else, if you are having any other doubts related to the any part of this week or the previous week sessions, we can discuss that also, and any other non-technical and technical query we can address it here. So let's start with our sample questions. So this week is currently being focused on the geosynthetics only. So basically the geosynthetics are the materials which provide a reinforcement in the soil so that it can take the tensile load coming over the soil. So soil, we know it's very good in compression, but it's very poor in tension and taking the tensile loads. So therefore we introduce the geosynthetic like materials which are basically made up of some polymers or some textile uh, sort of things in which can uh, bear the tensile load coming over the soil. So the first question for today is, which of the following fall under the classification of the geosynthetics? So you are having the four options: A, geogrid; B, geotextile; C, geonets; and D, all of this. Yeah, so the correct answer is D, all of this. So what else are the other geosynthetic materials we are having? We are having, one is the geogrid, then we are having the geotextile, we are having the geonets, geocomposites, geomembrane, geosynthetic ley liners, geocellular confinement system, geomats, geopipes, and geoforms. So these all are the geosynthetic like material available with us. The discussion about each and every geosynthetic type you can uh, see in the lecture notes given by the Professor Bedia. In there, he has very deeply defined the application of each geosynthetic material and what are its manufacturing is like and what is it's made up of. Coming to the next question, we are having which of the following is are the functions of geosynthetics? A. Reinforcement, B. Filtration, C. Erosion control, or D. All of this. Yes. Yeah, so the correct answer is D. Like geosynthetics can be used for the reinforcement also, as we have discussed earlier. Filtration process is another method where it can act as in draining out the excess pore water pressure, or if we are having the extra water table available, means the depth of the water table is very nearby the ground surface, then we can go for the filtration process. Also, since it's increasing the tensile capacity within the soil domain, so it will have a better interparticle strength by introduction of the geosynthetics within the soil. So therefore, we can prevent the erosion control also in the geosynthetics. So yeah, all of these are the correct answer. Other functions of geosynthetics, if we see, like reinforcement and filtration, we have already discussed. Also, geosynthetics helps in the separation of between the uh, soil layers. So for example, if we are having uh, one soil as a reactive soil or expansive soil, and if we want to prevent it from the other part of the soil, we can use it as a separation. And also drainage is the another criteria. So for example, pre-vertical drain, as we have discussed when we were dealing with the dewatering techniques in the previous sessions of the NPTEL course. So where we have seen that pre-vertical drains are basically the type of geosynthetic only. So it's helping us in draining out the extra or dissipation of the excess pore water pressure available within the soil. Also, we are having the erosion control, as we have discussed, like due to the introduction of the geosynthetics in the soil, we are basically increasing the interparticle friction between the soil, and therefore, whenever some shear force or the shear force, we can say there will be some shear at the top of the soil layer, the soil won't slide that easily if it would have been without the geosynthetics. Another example of geosynthetics is the barrier and the protection. So usually you guys would have seen that thing in the uh, hilly areas, or usually where the soil slope is very weak. So in that case, we used to introduce some sort of geonets or the geotextile materials at the slopey areas. So it basically prevents the falling of the soil over the root. So with the help of the barrier and the protection, we can uh, basically stop the flowing of the soil to the from the slopey or the hilly area. So these are some of the other functions of the geosynthetics. Any doubt in any part till now from any question? I guess it's just the theory part, so all related to the data only. But then also, if you want to discuss any points, please feel free to ask. No question, then okay, we can proceed to our next uh, sample question. So next we are having the mechanically stabilized earth wall. So what are the advantages of them? So select select from the options given below. Yeah, so the question is advantages of mechanically stabilized earth wall. So yeah, I guess we are having some answers. So let's check with that. Yeah, so the mechanically stabilized earth walls are basically the structure. I'll draw here. So let's so this is the wall available with us. So this wall is basically made up of some stones or modular bricks. This wall is further wrapped with some geosynthetic materials, if uh, you can see. Then if this is the reinforcement available with us, which is placed alternately with some compacted fill. So here we are introducing the compacted fill. So this whole mechanically stabilized earth wall is basically preventing the falling of the weak soil available here, which can uh, which can fall in the lateral direction if these walls are not have been provided. So as compared to the gravity wall and the other walls, this mechanically stabilized earth walls is very easy to build, and this is one of the advantages. Other advantages we can see means, since it's a very like simple structures, like you just need to introduce a wall here, then you need to introduce a compacted field with the alternately the reinforcement available with us. So it does not require any special contractors. You just need the specialty in materials, and then yeah, you are ready to go for constructing it. And as compared to the other slopey area where we want to prevent the falling of the soil, and this earth walls or mechanically stabilized earth walls are require very less space, because if there would have been slope here, it would need the extra space like this. So this extra space can be further prevented if we can introduce some mechanically stabilized earth walls. And since it does not require special contractors, it don't require the extra space, so definitely we are having the reduction in the cost. And since the whole structure is uniform, as you can see, so if there would have been the slope, we can expect there will be some differential settlement here, because the geometry here and here is different. But since the introduction of the mechanically stabilized earth walls, since it's having a uniform cross section area, so therefore we won't be having the chances of the, or like there will be very less chances of the differential settlement. So yeah, these are all are the advantages of the mechanically stabilized earth wall. Any query in this? Okay, let's move to the next question then. So in the previous question we have discussed about the advantages. Now let's discuss about the limitation of the mechanically stabilized earth wall. So yeah, with the same options available with you. So one of them is definitely odd one out, so you can select from the rest of three. Any query in any part, just discuss with me guys. Okay, let's check with the answer. So yeah, I guess yeah, there's problem with the answer. Sorry guys. One second, I'll correct it. So I guess correct answer will be the require high quality backfill materials. Yeah, so the correct answer is B option, that is requiring the high quality materials. So because definitely it's relatively easy to build, poor drainage is also one of the limitation, but yeah, in some case it will be there, it won't be there, but this high quality backfill material we required in every type of the mechanically stabilized earth wall. Therefore, B option is correct. Other limitations, if we can see, it's often require high quality backfill material. We have already discussed about it, and durability of the metallic and the geosynthetic reinforcement. So the as we have discussed, we are introducing. So when we are having the mechanically stabilized earth wall available with us, so if this is the compacted field, so this reinforcements is also having their durability. Means you can't rely on means this reinforcement will work in every situations due to some corrosive or due to the reactive nature of the material of this reinforcements. So therefore, we need to check with the durability of this material also. So this is another limitation. And poor drainage and global instability, yes, it can be the reason of one of the limitations. But this poor drainage, like again, it will depends upon the compacted field and the type of the soil available here. So in some case it will introduce the poor drainage, and in some case it won't introduce. So therefore, yeah, this is the, like we can say, it's little tricky about whether we should select this option poor drainage or not. But since it's not sure, so therefore we are ignoring here. So therefore we are only going with the high quality backfill material. Any query in this? This poor drainage part, I know it's little bit tricky because it would have come into the option, but yeah, if you see the pattern of the questions, all of this, if you would have select, this is coming the relatively easy to build option also, which shouldn't be the limitation, it's advantage. So therefore, if you go by the like question and answer round, you need to select the most appropriate option. So that is a B option. So let's move to the next question then. So now you need to find out the failure mode in which mechanically stabilized earth wall used to fail. So whether it's failing in the sliding or it's failing in the bearing failure, or we will have the overturning, select one of the option. So let's check with the answer. Yeah, it's all of the above. So other failure modes is basically if there are different type of failure modes Professor Bede had discussed. External, it's sliding, overturning, and the bearing failure. So let's discuss one by one. So sliding, I guess you know, if this is your wall, your lateral pressure is very high such that this frictional force can't resist it. So then we'll be having a sliding failure. Overturning failure, if the load apply here is having the eccentricity or the force is that much high such that the moment about this part, this moment which is being applied is not resisted by this moment at the base. So then we'll be having the overturning, and then we are having the bearing failure. So if the soil available here is very loose such that the mechanically stabilized earth wall is having very high weight from its on the soil, so this soil won't be able to bear the uh, load coming from the mechanically stabilized earth wall, so we'll be having the uh, bearing failure here. Then again there are some other failure modes also. So we are having the rupture, pull out, or the connection failure. So rupture is basically if you are having such that uh, your reinforcement available here. So if this won't be able to bear the tensile load coming over the wall, so you can see there will be the rupture or the breakage in the reinforcement. Then you are having the pull out failure. So this reinforcement along with the mechanically stabilized earth wall, due to the high lateral pressure, this whole system will come out. So this is another the pull out failure. Then we are having the connection failure. So connection failure, by its name you can know that this wall and this reinforcement connection, if it's not appropriate, yes, then we can also have the failure of the wall. Then we are having the local failure. So this is basically consisting of two, toppling and the bulging. So toppling is moreover is like the overturning criteria only. So if your shear force available here at the base of the wall, if it won't be able to resist the lateral force coming over or the movement coming over the wall, then we'll be having the toppling. Then we are having the bulging part. So if the mechanically stabilized earth wall, if it's very weak in the flexural strength. So for example, if this is the part, so your wall can have a bulging like nature here if the lateral force available is very high. So this is the bulging we can see. Then yeah, another form is the compound form of the failure mode. We are having the slow failure or the slip surfaces may be partially or fully out of the reinforcement zone. So let me draw it here. So here when the mechanically stabilized earth wall, if you are having the slope available here, sorry, not here, mechanically stabilized earth wall, you are having the reinforcement, and this is your soil domain. So and this is a slope. So there may be chances like there will be some slip surfaces here. Oh, let me draw it in the red. So we know in the slope failures we are having the slip surfaces available here. So this slip surfaces can be another reason for the failure of the this mechanically stabilized earth core, and therefore slope failure and slip surfaces may be partially or fully out of the reinforcement zone. So this can be into the reinforcement zone also, or we can have the slope failure above also. So this is the another area, and this global is basically, since it's happening like into the some domains of the uh, reinforcement region, this compound is when the whole soil available here will develop a particular slip failure. So there also will be having the slipping of the soil mass. So that is another failure mode. Any query in any part, please? So these are typical failure modes of the mechanically stabilized earth wall. These are similar to the, not particular similar, but moreover similar to the gravity earth wall. So only thing is like we are having the reinforcement available here in with the backfill materials. So that's why its failure mode is somewhat having higher number of failure modes as compared to the gravity earth wall. Any doubt in any part, guys? Am I clear? Can anyone please confirm am I audible or not? Yeah, thank you, Taman. So coming to the next question, the analysis of geosynthetic reinforcement earth wall is mainly based on. So you need to give the principal theory which from which we analyze the geosynthetic reinforcement earth wall. Yeah, so the Bhaskar is correct. These walls are basically analyzed with the help of the active earth pressure theory. So which we have discussed when we are dealing with the failure of the slope mechanism, or when we are discussing with the retaining walls. So where we have discussed like how the active earth pressure theory can be used in analyzing the stability of the earth walls. Let's move to the next question 7. So that was the theory part question. Any doubt in that? Okay, then let's move to this part. Seventh question. Which zone in the given figure is represented as active zone? So the correct answer is Y. The active zone will be the Y part. Let me show you this. So X will be the stable zone here. So we know, so if this is our wall and this is the range, or like, okay, it's not, it's enforcement as well. So this is a mechanically stabilized earth wall. So this wall is the wall available with us. So this region we know, this is the active region, and after some part the soil won't participate into applying the lateral pressure. So this we can say it's as a stable zone. So yeah, this is the nomenclature we usually give. This is the active region available with us, and this is the stable zone. Let's move to the eighth question. The lateral earth pressure coefficient for geosynthetic reinforcement. Eighth question, you need to define about the earth pressure coefficient for geosynthetic reinforcement. So how it's varying with the depth. So options are given with you. It decreases with depth down to 6 meter and then become constant with depth. It increases with depth down to 6 meter and then become constant with depth. Whether it's constant with depth or none of the above. So yeah, the correct answer is C. So the lateral earth pressure coefficient for geosynthetic reinforcement. So whatever geosynthetic reinforcement we are having, which we are providing within the soil domain. So if this is the soil domain, you are having geosynthetic reinforcement. For example, whether it's aligned in the vertical direction. So since this is the material, so its property won't change along the depth as we used to have into the soil part. So yeah, so the earth pressure coefficient for geosynthetic reinforcement is constant. Let's move to the next question. So 9th and 10th are basically theoretical question. So here we need to analyze the stability of the mechanically stabilized wall. So a vertical geosynthetic reinforced MSE wall is shown in the example figure below. The reinforcement field, the retained field, and the foundation soil have the same properties as shown in the figure. The traffic loading on the top of the wall is 20 kPa. ASTO design method is used to determine the required tensile strength of each geosynthetic layer. The required tensile strength for layer 1 is. So basically this is the typical cross section of a MSE wall. So the load coming from the transportation or the traffic loading is given as 20 kPa. So and the design code for designing this reinforced material is based on the ASTO code techniques. And now you need to determine the tensile strength for each layer of the reinforced layer. So first question is asked to determine for the required tensile strength for layer 1. So options, I guess okay. So yeah, the correct answer is D 9. Options are 7.2, 5, 10, 9. So just solve it from your end, then I'll show you what is the like how to solve this. I guess we are running short of time, so let me solve it for you. So this is the typical formula to calculate tensile strength is given as T1 max is equals to half K naught into gamma into the tributary length of the wall plus KAP into tributary length SV. So this KAI, so KAI you can calculate as tan square 45 minus 5 by 2. Phi is given as 30 degree, right? Yeah, Here you can see 5 is 30 degree. So 45 minus 5 by 2, 10 square, 30 by 2, 15, is 30 square. 10 square is 30, we know 10 30 is 1 by root 3, so it's 1 by 3.33. So, and gamma we know it's given as 20 kilonewton per meter cube, and since we need to determine the layer 1, so we know the tributary length. If you can see the diagram, the tributary length is basically given as 0.9 meter for the layer 1. So the total length plus first layer 1 along with the half of this part at the bottom. So this layer 1 will basically resisting the force for the whole layer 0.6 meter depth of soil and the 0.3 meter depth of soil below it. So we are having the tributary depth as 0.9 meter. So if we calculate the T1 max into the reinforced part, so it's given as half KAI. So KAI we know it's 0.33. Gamma is given as 20. Yeah, it's given as 20. H is zero point 0.9 square plus KAI is 0.33 again. This is basically KAI 0.33 into load coming from the traffic is 20 kPa. So the pressure is 20 here and the length is 0.9 meter. So if we will evaluate this, it's 2.6973 into 0.33 into 20 into 0.9. So you guys are getting like how we got this formula, right? So this is how much? Let me calculate this first. First 2.6973, it's around 8.6913. So yeah, it's typically to the 9 kilonewton per meter. So yeah, I was talking about how we got this formula. Let me discuss this. So this is your wall is available here. This is your reinforcements. So first of all, it is asked like you need to calculate the tensile force in this reinforcement. So this reinforcement basically will be resisting the whole lateral pressure coming from this soil plus half of this. So this depth is given as 0.6 and this depth is given as 0.3 meter, right? So from the soil we know the variation of the load profile will be triangular in shape. So this is the lateral pressure coming from the soil. So this will be your gamma H or gamma S I should say. So that's how, and the lateral pressure will be K naught gamma S. So the vertical will be gamma S and the lateral we know it's the K naught time gamma S. So This is the half into K gamma square. So this is the area of this triangle. We know this is the S. And then we are having the load coming from the traffic. So load coming from the traffic, it's having the magnitude of the P, and the total depth we know is given as S. So the area of this, sorry, this is the K naught time P. Again, sorry, because the P will be the vertical pressure, and now we are talking about the lateral pressure. So K naught times P. So this is how we got the formula for this. Ki you can evaluate from this 10 square 45 minus 5 by 2 from the Rankine theory. Then we are having the T max. T max, we need to find the area of these two loading diagrams. So that's how you got the tensile load in this reinforcement. Any query in any part, guys? Like, I know I have rushed through this, but since due to the time constraint, but yeah, if also you are having any doubt in this, shoot it. Yeah, so basically it's you need to find the load in this tensile reinforcement, which will be basically resisting the load coming from the soil lateral earth pressure and also the load coming from the traffic load. So these two will be resisted by this reinforcement. Okay, no doubt. Then let's move to the final question of the day. For the data given in the above question number 9, the required tensile strength for layer 3 is. So option is 11.2, 10.2, 15.2, 16.2. I guess there's some mismatch between my animations. So, but yeah, answer is 11.2. So again, the same theory will be followed as we have discussed in the previous part. So let's have 4 minutes for you guys to solve this. Otherwise, I'll be solving this. No problem. Guys, ask if you are having any doubt, please. The time given by NPTEL team is 6 p.m., right? I can see people joining at 7. I don't know why. Anyhow, if you have missed this part, these videos are recorded. You can check it on the YouTube channel link, which is shared by the NPTEL team. Also, I'll be uploading the PDF format of this slide, so you can check some of the solutions which I have solved it here. So no problem in that. Okay, last question, guys. Like earlier, we have solved it for the layer 1. Now you need to solve it for the layer 3. Due to my animation problem, I have already given the answer for this question, but try with this thing. Okay guys, I know you can solve this. Let me solve it for you. So it's similar to the previous question only a little part in the traffic loading, like how you will consider that. So let me solve it for you. So this is the question you are having. This is your wall, right? Oh, sorry with my drawing, it's very bad, I know. This is the wall. Then you are having the reinforcement here. So this is 0.6 meter. This is zero point 0.6 meter. This is zero point 0.6 meter, right? And this is your soil domain available with you. This is your backfill available here. Earlier we have calculated the reinforcement force in tensile force in this reinforcement. Now you need to calculate at this reinforcement, which is located at depth, or we are calling it as a layer 3. So how to proceed with this? So the formula used will be the same, like you will be having the two loading available, which will be basically registered by this. So T3 can be given as, so like let me proceed with the diagram first. So if you can see here at this part, you will be having two loading. One will be the traffic loading, and then you are having the lateral pressure from the soil. So lateral pressure from the soil, we know it will vary from this part. So the total vertical pressure, we know it's the gamma times H, and therefore the vertical pressure will be Ki times gamma naught H. So this is basically the depth is H only. So the loading will be from the lateral pressure. Now let's check the traffic loading. So we know the traffic loading is having the profile like this. So the magnitude is given as Ka times P. So P is the traffic loading which is being applied at the top. So the trick part is here. So now tell me, should I consider this whole area while evaluating the tensile force in this? Okay, let me ask in this way. So this traffic loading is also divided into three parts for the different layers. So there can be two options. Either I should consider this whole area while evaluating the tensile force in this, or I should consider only this part. So which option? First one or the second one? So okay, no problem. So while evaluating the traffic loading, we will consider only this part, like because the other load is already being registered by this reinforcement, but this reinforcement will only be taking care of the traffic loading domain which is coming over this part. So therefore if we will calculate the total load T max, so it's the half time H is given as 1.8. So this is basically half into Ka gamma into H square plus 1 by 3 gamma into H square plus 1 by 3 into Ki, sorry, so we know the area is half into H into Ki into gamma naught into H, right? So for this triangular area, and this we are having Ki into P into only 0.6 meter we will consider, so this is 0.6 the tributary area for this. So if we will evaluate this, half into H, H is how much? 1.8 into Kai, we know it's 1 by 3, gamma is 20, height we know it's 1.8 only since we are evaluating in this. Then we are having 1 by 3, P is 20 and it's 0.6, and also we'll be having the H also, sorry. So this is H is 1.8. So basically we are calculating the pressure here, Ki gamma into H. So 1 divided by 3, answer into 20 into 1.8. Of into H, Ka guys. 1 second guys. Okay, so basically we are calculating at the layer 3 here, not at the tensile reinforcement. So what we need to do, like sigma H we need to calculate. So this is Ki times into P coming from the traffic loading. So first we need to calculate what is the pressure coming here. Then that pressure we can apply, multiply it with the tributary load to calculate the tensile force in this. So Ki into P will be the tensile force pressure coming from the traffic loading. Then we are having the Ki into gamma naught into H. So this is the part. So Ki we know it's 1 by 3, P is 20, 1 by 3 gamma naught 20 into height is 1.8. Total height we are saying. So this is basically, if you calculate this is 18.48. So this is the total pressure acting here. Sorry guys, I was wrong with this. So 18.48 kPa is the total pressure acting here. And then if you want to calculate the load in this, so that load we need to multiply with the tributary length available here. So which is the 0.6 meter. So T max is equals to 18.48 into 0.6. So this is basically equals to 11.2 kilometer meter. So yeah, A option is the correct answer. I made a slight calculation problem in this, but yeah, this is how you will proceed if you are having this type of questions. Any query in this, guys? Means you are calculating this KIP force here, then KI gamma naught H pressure here, then this two pressure you are basically multiplying it with the whole tributary length to get the tensile distance. So this pressure you will distribute throughout the tributary length. Similar we have done in the previous question also. So we have calculated the first pressure at that depth with the soil domain, then with the traffic loading, then we have multiplied it with the whole tributary length available. So the only part is that tributary length and the total depth is same here, but here the tributary length and the total length is different here. So that's why we have calculated like this. Okay guys, so if you are having any question we can discuss, otherwise let's wind it up for today. Let's meet on next Tuesday at same time at 6 p.m. So next week I guess we'll be having the last lecture of this NPTEL session. So if you are having any query throughout the course, you can bring it up and we can discuss that thing in the next session. Okay guys, thank you.